Okay, this video is going to introduce the chapter on benzene substituents. Before we started with new stuff, let's take a look at some review. In chapters 15 and 16 we talked about reactions with benzene, and we know that in order to add a halogen you need that iron bromide catalyst. If you don't have it, you will have a no reaction. Much earlier in the course, way back in 118A, we talked about radical reactions with halogens, and that they could substitute out a hydrogen through a free radical mechanism. We would have more of the 1-chloropropane because we have a methyl group on each end, so more available hydrogens to create that. We're going to combine these reactions for the first part of our benzene substituents chapter. We're going to combine those two concepts using heat, light, and a halogen to allow us to attack a methyl group off a benzene ring. So we can take a halogen just using heat and light and end up replacing one of those CH bonds with a C halogen bond, in this case a C bromine bond. We can do this with both bromine and chlorine, and if we have extra time and extra temperature, we actually can get multiple substitutions at the same carbon, even getting a tri-substituted carbon. Why does this happen? Let's take a look at the mechanism for why this happens. Remember, for free radicals, all our arrows for this part is going to be drawn with a half arrow, also known as a fishhook arrow, because it's tracking single electrons, no longer electron pairs. So here I've already generated the halogen free radical. It's going to come react, pull off that hydrogen, creating a molecule of acid and a carbon radical. Why does this happen? This CH bond actually is stabilized through resonance with the benzene ring. So you can imagine a structure that looks like this. So this is not just your simple methyl group having a radical. It's stabilized throughout the entire ring. This structure then gives a carbon radical that then come and generate another halogen radical that will then continue and propagate this chain. So you'll be left with a monohalogenated product. We can also do this knowing that we create a bold and a traditional methyl radical. We can also see this with carbocations as well. So if we have a methoxy group on our benzene ring and a great leaving group, we can see an SN1 reaction through the generation of a carbocation. Let's look at how these structures actually would look via resonance. So if our leaving group leaves, we can then push electrons out on to our methyl group, stabilizing the carbocation with the ring. We can then move these electrons around, out into and including our methoxy group. So the methoxy group actually helps stabilize this carbocation, adds to this mechanism. If we don't have the methoxy group, remember, we're still able to stabilize that entire charge throughout the benzene ring. So here, we're not going to be able to generate a carbocation, but we can do an SN2 reaction where our nitrile group can come in, attack, kick out the bromine, and now we're left with a nitrile group off the carbon on our benzene ring. This is a nice reaction because we know lots of new chemistry we can do with nitriles based on our last carboxylic acid derivatives chapter. A couple other reactions. This one we've already talked about, potassium permanganate adding a carboxylic acid at any benzylic hydrogen position. So this will happen in both places as long as there's a hydrogen attached to that first carbon off the ring. The next reagent does the same thing, except it works with benzylic alcohols and turns them into ketones. Check back for more in the next video.